Next up, we have Scott Collis, who's going to be introducing SAGE, Cyber Infrastructure for the Nation, pushing AI to the edge.
Thank you very much, Jennifer, and thank you to Joe and the committee for giving us time to present this. Are you able to see my slide in presenter mode?
Yes.
Excellent, thank you. So I won't go through the author list. We have a cast of thousands here, but this work I'm about to present is supported by the National Science Foundation Office of Advanced Cyber Infrastructure and Argonne Laboratory Directed Research and Development, and is work across Argonne and Northwestern University through the Northwestern University Argonne National Laboratory Institute of Science and Engineering. So an outline to my talk is, first of all, I want to motivate the need for edge computing. I want to tell you what edge computing is, describe the concept of cyber infrastructure, introduce the SAGE continuum, and cover the science that can be done with SAGE and highlight several student and postdoc examples. This is our 2020 group photo of the SAGE student team taken under COVID-19. So when you're seeing these student projects, keep in mind these were all pretty much done over Zoom. It has been a very unique experience mentoring students. So for this audience here, I'm going to give you a very brief motivation. You all know this. The challenges of measuring our planet is connecting the vast scales of the processes that influence Earth system predictability, from hurricanes down to ice, snowflakes and aerosols, and even smaller. Ironically, most of these scales are measured with cameras, to some that are really, really close and some that are far away. So the two challenges that we have from an instrument and observing perspective: how do we do the best processing in a bandwidth limited instrument, such as instruments we might have up at the North Slope of Alaska, where we're not able to send everything back, but we want to preserve the information content there. And for an instrument that makes decisions about spatial or temporal sampling, how do we run an instrument in the right mode for the science question being asked and the phenomena that is present? So edge computing it's exactly what it says it is. It's pushing the CPUs, GPUs, TPUs right up against the instrument. A supercomputer is a device for turning compute-bound problems into I/O-bound problems. Anyone who's ever done any HPC knows 9 times out of 10 when you're doing data analysis, your challenge is getting it off the storage device as efficiently as possible. An edge computer is a device for turning I/O-bound problems into compute-bound problems. You can push as much infrastructure as you can right up next to the instrument, but you then run into the challenges as you can no longer have, exascale computing in the end. So cyber infrastructure. Cyber infrastructure actually was first termed in a defense, actually by the predecessor to DHS, but it was first used in a science perspective by the National Science Foundation. And it basically refers to the common hardware and common software that can be used by as many of the nation's scientists, engineers, scholars, and citizens to achieve the science they want to achieve. So when we talk about cyber infrastructure and our project I'm going to introduce here, we are focused on that common hardware stack and common software stack for doing edge computing with a well-defined interface. We're really keen to leave the science, the user-provided stuff, and the domain applications to you, to domain scientists, DOE, NSF, NASA, PIs. We're focusing on that linchpin application. How do we hit as many goals as possible, not just in the earth sciences, but actually across science in general? So I'd like to introduce SAGE. SAGE is a multi-institutional collaboration aimed at providing cyber infrastructure for the nation. We're led by Pete Beckman from Northwestern University and Argonne, and we have a variety of target user facilities, including NEON, HPREN, the Array of Things, and the Urban Wildlife Institute. And you can see a bunch of sites that we're targeting across the US for our initial deployments. You'll also notice a couple of ARM-ish looking sites. Bobby Jackson's going to talk about a parallel project called Arming the Edge, which is aimed at tailoring some of this work to the needs of the ARM, which is supported by laboratory-directed research and development. So when I talk about AI at the edge, what do I mean? So there's been an explosion of small compute devices, including NVIDIA Jetsons, Google's tensor processing units, that we can push right up against the edge. So we take data sets from various sensors, including cameras, LiDARs, hopefully eventually radars, and we can train neural networks to, for instance, predict the motion of cells, predict the cloud cover and stuff like that, which I'll talk about soon, train on HPC, create the neural networks, which as we know are quite small in size, and then push them to the edge. And have basically, and we've talked a little bit this week about reinforcement learning, we can also do this kind of reinforcement learning, push data sets back to HPC and then push them to the edge here until we can actually really have, especially when we talk about 5G, a continuum of compute and networking. So what does cyber infrastructure look like when we talk about SAGE? And I'm not going to have time to go through all of this because I am a little bit through already. We talk about building, basically being able to have people submit code, mainly through Dockerization, train it locally. We actually have a virtualized instance stood up on a HPC cluster at the University of Chicago. Feed data sets into it, see how the decision making goes at the edge, for instance, to detect whether a particular phenomena is present, and then to be able to schedule it and run it at the edge. Now, this is my hopelessly complicated diagram that I'm not going to describe at all. All I want you to take away from this is we're 1 year into this project, and most of our staff are really focused on the infrastructure that sits underneath that user level. How do we do the scheduling? How do we deal with things like multi-tenancy, deciding which science question actually deserves the greatest CPU or even instrument resources? So a lot of this is being thought about and being designed right now. But when you're designing an infrastructure like this, this can't just be designed by computer scientists. It needs to be designed by folks that understand the science as well. So to do this, we created a series of science exemplars questions. You can see them listed here. Some of them are convergent, some of them are focused on the NEON network, some of them on HP-RAN, and some of them on the array of things. And they're driven by affordable instrumentation because our original scope was cut down, and unfortunately we lost a couple of PIs and funding that would have given us scanning Doppler LiDARs. As part of that, we then focused on pan-tilt zoom cameras as an analog for scanning instrumentation. Let's go. And again, as I said, ARM is one of our science exemplars, but Bobby will talk about that next. Here, this is graphically a couple of our exemplar things, including pedestrian flow, drone detection, really keen on snow depth, which I think would be awesome for the North Slope of Alaska for looking at ground state. Of course, NEON uses white stakes as snow stakes. So that's one thing. We had a person go out with a Sharpie and fix that for us as soon as we can. So anyway, many ways to help us design a cyber infrastructure. And we really leverage students this summer to help us push this. So one of our students was Rick Nueve. Rick came to us from the Northern Illinois University, and Rick wanted to know if I had a upward pointing camera and a temperature camera that measured the skin temperature of foliage and also clouds in the sky, can I build a network that will actually help me forecast solar radiance as detected by a radiometer at Argonne? So Rick built a network and trained it. He used an LSTM layer to encase temporal information, next frame guessing, and he got some pretty pleasing first results. One interesting thing, when we had our FLI image, we had to segment the ground and the sky because the ground and the sky respond very differently to overcast versus sunny situations. We have a postdoc, Songho Park. Songho actually has money from our local energy consortium to try to predict solar radiance or try to turn an upward facing sky camera into an Radiance detector. You know, Chuck Long, if he was with us, would point out the true challenge of this, optically thin clouds, and we've run into exactly the same problem. But basically, we're trying to do cloud fraction from these. And basically what I've done is I've come in and hijacked her project. We're going to be sending these FLIR and PTZ cameras out to SGP. And we're really keen to see how we can use ARSCL to train a network for doing these kind of things. So Songho's really looked at a whole variety of different networks and techniques for predicting that. And our final example I'm going to very briefly show is from Nalishi Vara. We're working with Aaron Kennedy from the University of North Dakota, who has a camera that takes snowflake images, and we wanted to build a network to do automated habit and counting of snowflakes. And so Nalishi's initial work, we've got a testing accuracy of around about 72%. We really want to apply layer-wise relevance propagation to understand why it's classifying certain snowflakes correctly and incorrectly. And we're also looking at you only look once, YOLO, for image segmentation and doing PSDs from Aaron's camera there. So status, these images are from June, so we've got a lot further there. This is what an outdoor node looks like, or what we call our wild sage node. I want you to focus on this device here. This is called our Waggle controller. This looks after all the TPUs, Jetsons, Raspberry Pis, Arduinos underneath that, and will automatically do things like flashing firmware, health and status, bringing them up. And this is where the investment has been going into building 100-year shuttle robust technology. Here's an example on our outdoor units with a pan-tilt zoom camera up the top. We are going to be deploying one of these to SGP, and I'm really excited to see what we can do with these pan-tilt zoom cameras. Thank you very much for Operation Warp Speed, an introduction to SAGE and the work we are doing. You can contact me. I'm on Twitter there, or you can, as Amy said, we have a Twitter handle, but it's just me right now. So what we're looking for from you and why I'm giving this talk, we're really interested in working with you on student projects, looking for cool instruments to apply Edge to. And if you have a need for a cyber infrastructure partner in a proposal, give us a yell. We're very interested in growing this and really tackling the linchpin problems. So that's it.
Okay, thanks, Scott. Right on time. Are there any questions for Scott coming up in the chat? I don't see any yet.
Yes, just like Amy, I can't see the chat either.
You can't, yeah, you can get out of present.
Oh, I know I can stop sharing. That's what I can do. Now yeah, I can see the chat.
Yeah.
Awesome. Nope. Okay. Anyway, folks, I imagine most people know who I am, so you can contact me later. I will add, since I've got 2 minutes left, another really interesting project we're tackling is using software-defined radios for lightning detection with Eric Brunning, which I cut out of this talk because I was worried I would run out of time. So we're going to be deploying a couple of nodes to Tracer as well, not as part of the ARM part, but actually working with the University of Houston. So if anyone's interested, and I've talked to Scott Giangrande about building a Houston camera network for doing, again, more looking at clouds with both the stereo cams, but then integrating in these infrared cameras as well. So thanks, Jennifer.
Okay, thank you, Scott. I think we'll move on then. Feel free to submit any questions to the chat